Somewhere in a lab in Santa Barbara, California, there is a machine that has to be cooled to a temperature colder than deep space. It hangs in a gold-plated chamber like a chandelier, wired with thousands of cables, humming at a fraction of a degree above absolute zero. Inside it, something happened in late 2025 that made physicists stop and reread their own data twice. Not because a machine had become conscious, not because it had literally glimpsed tomorrow, but because it had done something that, on the surface, looks disturbingly close to rewinding time itself. And in doing so, it exposed a pattern in the universe that most people don't know exists. A pattern that governs everything from the shuffling of a deck of cards, to the decay of a star, to the way a rumor spreads through a crowded room. This is the story of Google's Willow chip, the algorithm called quantum echoes, and the strange mathematics of chaos that connects them. And by the end, you'll understand exactly why some of the smartest people on the planet are choosing their words very, very carefully when they talk about what it found. Let's start with the headline, because the headline is doing a lot of work. A mathematical pattern that predicts the future. It sounds like science fiction. It sounds like the kind of thing that should come with a warning label. And in a way, it should, not because it's false, but because it's easy to misunderstand. So before we go further, let's be precise about what actually happened, and then let's sit with why it's genuinely one of the strangest and most important experiments in modern physics. Quantum computers are not really computers in the way your laptop is a computer. Your laptop stores information as bits, ones and zeros, tiny switches that are either on or off. A quantum computer stores information in qubits, and a qubit can exist in a strange in-between state, a blend of 1 and 0 simultaneously until the moment you measure it. When you link many qubits together, they can become entangled, meaning the state of one qubit is tied to the state of another, no matter how far apart they are or how complicated the system becomes. This is the property Einstein once called spooky, and it is the beating heart of everything that follows. Google's quantum processor, nicknamed Willow, is built from just over 100 of these superconducting qubits arranged on a chip barely the size of a coin. In late October of 2025, a team led by researchers including Michel Devoret, Vadim Smolyansky, and Hartmut Nevin ran an experiment on Willow that they called quantum echoes. The name is almost too perfect because what they were doing was, in essence, sending a signal into a storm of quantum information and listening for its echo. Here's the experiment in plain language. Imagine you have a Rubik's Cube. You scramble it with a long, complicated sequence of twists. The cube looks like chaos now, colors scattered everywhere, no trace of its original order visible to the eye. Now imagine that in the middle of that scrambling sequence, you sneak in one extra twist, a tiny, almost invisible nudge that wasn't part of the plan. Then you run the entire sequence backward, undoing every twist in reverse order, trying to return the cube to its solved state. If your extra, hidden twist made no difference, the cube would return to perfect order. But it doesn't. That one small disturbance, buried in the middle of the chaos, leaves a mark. When you unscramble everything, the echo of that tiny nudge is still there, distorting the final result in a way you can actually measure. That's exactly what the Google team did, except instead of a physical cube, they used the quantum states of over 100 entangled qubits. And instead of twisting colored squares, they were applying carefully choreographed quantum operations. They sent a signal rippling through the lattice of qubits, let it scramble into what looks, from any single vantage point, like total randomness, then nudged one qubit ever so slightly, a quantum version of the butterfly effect, and reversed the entire process. What came back was an echo, a faint, buried in noise, but unmistakably there, a trace of that one small disturbance rippling out and then rippling back, carrying information about how it had spread. Physicists have a formal name for the quantity that measures this rewind and compare trick. They call it an out-of-time order correlator, or OTOC for short. It's a mouthful, but the idea behind it is beautifully simple. It measures how fast information scrambles inside a complex, interconnected system, and how much a small disturbance early on ends up shaping everything that comes later. Google's team didn't just measure one OTOX, they measured a second-order version, effectively running the scramble-unscramble sequence twice in a row, which amplified the tiny signal until it became clearly visible above the background noise. It's the difference between whispering into a canyon once and hoping to hear a faint echo, versus whispering twice in a specific rhythm so the echo comes back loud and clear. Now here's the part that made headlines. Google compared how long this measurement would take on Willow versus how long it would take on the world's most powerful classical supercomputers, machines like Frontier, currently among the fastest number crunchers on Earth. According to their published results, the quantum processor completed the calculation in a matter of hours. The classical supercomputer, running the best-known algorithms for the same task, was estimated to need approximately 13,000 times longer. Some estimates for related, but even more complex versions of this calculation stretched into numbers that dwarf the age of the universe many times over, a figure so large that writing it out in years is almost meaningless to a human brain. To be clear, that comparison is specific to this narrow class of problem, the interference-heavy scrambling calculations that grow explosively complex as you add more qubits. It is not a claim that quantum computers can now outperform classical computers at everything, or even at most things. But for this specific class of calculation, one tied directly to how chaos and information behave in complex systems, the gap is not small. It is closer to unbridgeable with today's classical hardware. So why does any of this matter beyond a laboratory curiosity? Why are physicists using words like disturbed and unsettled instead of just impressed? Because scrambling, the thing this experiment actually measures, is not just a quantum computing party trick. It is one of the deepest and strangest concepts in all of physics, one that connects the inside of a black hole to the shuffling of a deck of cards to the reason you can't unscramble an egg. Let's talk about why. In everyday life, we take for granted that some things are reversible and some things are not. You can rewind a video of a bouncing ball and it looks perfectly normal played backward. But rewind a video of an egg cracking on the floor, splattering into a mess and playing it backward looks absurd, impossible, like a magic trick. Physicists call this the arrow of time, and for a long while the explanation was mostly statistical. There are vastly more ways for a system to be disordered than ordered. So as time moves forward, systems drift toward disorder simply because disorder is so much more probable. This is the second law of thermodynamics, one of the most unbreakable rules in all of science. But scrambling, in the quantum sense, digs one layer deeper than ordinary disorder. It's not just about entropy increasing. It's about information itself becoming hidden, smeared out across the system so thoroughly that it becomes, for all practical purposes, unrecoverable, even though, in a strict mathematical sense, it's still technically there. Think of dropping a single drop of ink into a glass of water. At first, you can clearly see the drop, a distinct blob with a clear boundary. Stir the water, and the ink disperses. After enough stirring, the ink is spread so evenly throughout the glass that you can no longer tell where it started. The information about the ink's original position hasn't been destroyed, not in the strictest physical sense. Every water molecule technically still remembers a trace of that original interaction. But recovering that information by looking at the now uniformly tinted water is, in practice, impossible. It has been scrambled beyond recognition. This is precisely the phenomenon physicists have discovered inside black holes, inside chaotic quantum systems, and now, measurably, inside Google's Willow chip. When information falls into a black hole, current theory suggests it doesn't vanish, but it scrambles, spreading across the black hole's internal degrees of freedom so thoroughly and so fast that reconstructing it from the outside becomes, in practice, impossible, even though physics insists it must still be there, encoded somewhere in the outgoing radiation. Black holes, in fact, are theorized to be the fastest possible scramblers in the entire universe, a kind of cosmic speed limit on how quickly information can be hidden. What Google's experiment did was create a small, controllable, laboratory-sized system that scrambles information in a mathematically similar way, and then, remarkably, unscramble it, revealing the ghost of the original disturbance still tucked inside the noise. This is where the predicts the future framing comes from, and it's worth being honest about both its poetry and its limits. The experiment does not let you see next week's weather or next year's stock prices. It cannot tell you who wins an election or whether it will rain on your birthday. What it does is far stranger and, in its own way, more profound. It demonstrates that a small, precise nudge introduced at one moment can be traced mathematically all the way through a chaotic, scrambling process, and recovered on the other side. In systems that behave chaotically, tiny disturbances early on cascade into enormous differences later, the same butterfly effect immortalized in weather prediction and chaos theory. The Willow experiment essentially proved that even inside a system so scrambled it looks like pure noise, there remains a precise, calculable pattern connecting the past disturbance to the future outcome, one so exact it can be measured, verified, and reproduced. That's the pattern that predicts part, not a crystal ball. A mathematical structure hidden inside chaos that lets you trace cause and effect through a system so complex that, until this point, no computer on Earth could reliably do it. And that distinction matters enormously because it's the difference between mysticism and physics. Physics doesn't need to claim it can see the future to be unsettling. It only needs to show that the line between unknowable chaos and calculable pattern is not where we thought it was. Now, let's talk about why physicists reacted the way they did, because disturbed is a strong word, and strong words in science usually come from a very specific place. Not fear of the unknown, but the uncomfortable feeling of watching your own assumptions get tested in real time. For decades, out-of-time order correlators were almost entirely theoretical. They appeared in papers about string theory, black hole thermodynamics, and quantum gravity, places where physicists build elaborate mathematical frameworks, because they have no way to run the actual experiment. You couldn't scramble a black hole in a lab. You couldn't watch information disperse across an event horizon and then, impossibly, watch it get reconstructed. OTOCs were a theorist's tool, a way of writing down what should happen according to the equations, without any real hope of watching it happen with your own eyes, in a controlled setting, with dials you could turn and errors you could quantify. Willow changed that. For the first time, researchers could dial in the exact parameters of a scrambling system, control precisely how much time passed, how many qubits were entangled, how strong the disturbance was, and then watch, with hard experimental data, whether the theoretical predictions held up. And they did. Precisely. That is the part that should give you pause, in the best possible scientific sense. It's one thing to trust an elegant equation. It's another thing entirely to watch that equation play out on real hardware, with real noise, real imperfections, real measurement uncertainty, and have it match anyway. There's a deeper layer to this too, one that connects quantum computing to an idea that has quietly become one of the most talked about concepts in modern physics. The notion that the universe itself might, in some deep mathematical sense, behave like a kind of information processing system. This isn't a claim that reality is a simulation in the science fiction sense. It's something more subtle and, honestly, more interesting. Physicists studying black holes discovered that the amount of information a region of space can hold is proportional not to its volume, as you'd naively expect, but to the area of its boundary, a strange result called the holographic principle. Around the same time, physicists studying quantum chaos discovered that black holes scramble information as fast as the laws of physics allow, sitting at a theoretical speed limit that ordinary chaotic systems approach but rarely reach. Google's OTOC experiments are, in effect, one of humanity's first controlled glimpses into that same scrambling behavior, run not inside a collapsing star, but on a chip you could hold in your hand. That's the disturbing part, if we're being honest about the word. Not that a machine predicted the future, but that a laboratory experiment sitting on a benchtop in California is now producing data relevant to some of the deepest open questions about black holes information and the fabric of space-time itself. Questions that used to belong entirely to chalkboards and thought experiments now have an experimental foothold. That's not a small thing. That's the kind of moment physicists wait entire careers for. There's also a very practical, very human reason scientists are paying close attention, and it has nothing to do with cosmic mysteries. It has to do with what this technique can actually build. The same echo protocol that measures information scrambling turns out to be extraordinarily useful for a much more grounded application, peering inside molecules. Researchers use a technique called nuclear magnetic resonance, or NMR, to study the structure of molecules by measuring how atomic nuclei interact with each other, essentially building a map of a molecule's internal architecture. But NMR has always had a range limit. Two atoms have to be close enough together for their magnetic interactions to be detectable, which puts a hard ceiling on how much of a molecule's structure you can map at once, especially for large complex molecules like proteins or novel materials. Quantum echoes offers a way to extend that range. Because the algorithm can amplify faint interference signals that would otherwise be lost in noise, it effectively builds a longer measuring stick, letting researchers detect interactions between atoms that are farther apart than traditional NMR could ever resolve. Google's team demonstrated this isn't just theoretical by running actual molecular structure verifications, comparing results from Willow against known molecular geometries and getting matching answers. If this scales, and that's a genuine if, requiring further advances in qubit count and error correction, it could eventually help chemists design new drugs, new materials, and new industrial catalysts by giving them a far more detailed picture of molecular structure than current tools allow. That's not science fiction. That's applied chemistry, pharmaceuticals, and materials science, all potentially inheriting a tool built from an experiment about time reversal and quantum chaos. It's worth pausing here to underline something important, something that separates real physics from the more breathless corners of the internet. None of this means quantum computers are about to replace your laptop, solve every mystery of the universe, or achieve some kind of godlike predictive power. The advantage Google demonstrated is narrow and specific. It applies to a particular category of calculation, one involving deep interference effects between huge numbers of quantum possibilities, a category that happens to be almost impossible for classical computers because the complexity grows exponentially with every added qubit. Classical computers remain better, faster, and vastly more practical for the overwhelming majority of tasks humanity actually cares about, from spreadsheets to video games to training everyday AI models. Quantum advantage, where it exists, is a scalpel, not a hammer. It works spectacularly well on a narrow set of problems that happen to be perfectly shaped for how qubits behave, and it remains, for now, largely unproven outside of that narrow set. There's also the matter of verification, which is a subtler, and in some ways, more philosophically interesting question raised by this whole line of research. When a classical computer produces a result, you can, in principle, check its work step by step, since every operation is deterministic and traceable. Quantum computers are different. Their power comes precisely from processes that are probabilistic and, in a sense, unknowable in fine-grained detail until measured. So when Google claims Willow performed a calculation faster than any classical machine ever could, how do you actually confirm the answer is correct? If no classical machine can independently redo the same calculation in a reasonable amount of time to check it? The Quantum Echoes team addressed this by cross-checking their results against known physical systems and smaller-scale calculations that classical computers could still verify, essentially building confidence at manageable scales before trusting the result at the full, unverifiable scale. It's a clever workaround, but it also opens a strange epistemic door. We may be entering an era where some of our most advanced computational results simply cannot be double-checked by any other means. And we have to trust the process, the physics, and the statistics instead of a direct line-by-line verification. That, too, is part of why some physicists describe this moment as unsettling. Verification, the very bedrock of the scientific method, is being quietly redefined by machines that can compute things no other machine can independently confirm. Let's bring this back to that word future one more time, because it deserves a fuller answer. The pattern Google's experiment revealed isn't a fortune-telling algorithm. It's something arguably more remarkable. Proof that even in systems complex enough to look like pure randomness to any observer, there exists an underlying mathematical structure connecting a disturbance at one moment to its consequences later on. A structure precise enough to calculate, measure, and reproduce. This idea that chaos is not the absence of pattern, but a deeper, more hidden kind of pattern, is not new to physics. It echoes through chaos theory, through weather prediction, through the strange attractors that govern turbulent fluids, through the mathematics of how epidemics spread and how ecosystems shift. What's new is that, for the first time, we have a machine capable of running this kind of calculation on a system with more possible internal configurations than there are atoms in the observable universe, and getting an answer that matches physical reality. If you zoom out far enough, the story of Quantum Echoes is really a story about humanity building its first genuinely reliable window into the mathematics of chaos itself, the same chaos that governs black holes, that governs how information can be hidden and recovered, that governs how a butterfly's wing beat, in principle, could nudge a hurricane thousands of miles and weeks away. We've always known in the abstract that chaotic systems obey precise underlying laws. What we didn't have until very recently was a tool capable of tracing those laws through a system complicated enough to actually resemble the messy, entangled complexity of the real world. That's not a machine predicting your future. That's something almost more interesting. It's evidence that the universe, at its most chaotic and scrambled, is not actually lawless. It's playing by rules precise enough that, with the right tool, you can watch a whisper of disturbance ripple through chaos and come back out the other side. Recognizable, measurable, real. Physicists aren't disturbed because they've seen something that shouldn't exist. They're disturbed in the way scientists get disturbed, which is really a kind of electric, uneasy excitement because they're watching, for the first time in real experimental data, a confirmation of ideas that used to live only in chalk equations about black holes and information theory. They're disturbed because a benchtop chip, cooled colder than outer space, just handed them a working, measurable model of some of the strangest physics in the universe. And they're disturbed because they know this is very likely just the beginning. Willow has just over 100 qubits. Future chips will have thousands, then millions. Each added qubit doesn't just add a little more power, it multiplies the space of possibilities exponentially, meaning the gap between quantum and classical computation, already vast for this class of problem, will almost certainly grow wider, not narrower, as the technology matures. So the next time you see a headline that says, "A machine predicted the future," here's the more accurate and honestly more fascinating version of the story. Scientists built a device that can scramble quantum information into what looks like total chaos, then rewind that chaos and recover a hidden signal buried inside it, faster than any other computational system on Earth, by a margin so large it barely fits into ordinary numbers. In doing so, they've opened an experimental doorway into questions that used to belong entirely to theoretical physics: how information behaves inside black holes, how chaos and order coexist inside the same mathematics, and how much of what looks like randomness in our universe is actually a precise, traceable pattern waiting for the right instrument to reveal it. That instrument now exists. It's sitting in a lab, cooled near absolute zero, and it just gave physicists their first real reproducible glimpse into the mathematics of scrambled reality. Whether or not you want to call that predicting the future, it's undeniably one of the strangest and most important experiments of the decade, a genuine crack in the wall between theory and observation, and a signal, quite literally an echo, that the deepest mysteries of physics are finally becoming things we can measure instead of just imagine. Let's slow down for a moment and talk about why this particular chip, Willow, has become such a lightning rod for these kinds of headlines in the first place, because its history matters. Willow wasn't Google's first quantum processor, but it was the first to cross a threshold engineers had been chasing for years, a property called below-threshold error correction. In earlier quantum chips, adding more qubits also added more opportunities for errors, since qubits are extraordinarily fragile, disturbed by stray heat, cosmic rays, or even faint vibrations from a passing truck outside the lab. For a long time, the more qubits you added, the worse your error rate got, which meant scaling up a quantum computer was, in a strange way, self-defeating. Willow demonstrated the opposite. As researchers added more physical qubits to form a single, more robust logical qubit, the error rate actually went down, exponentially, with each added layer. That single result, published before the Quantum Echoes experiment, was already considered one of the most important quantum computing milestones in years, because it suggested that scaling toward a truly fault-tolerant large-scale quantum computer was not just theoretically possible, but practically achievable with existing engineering approaches, rather than requiring some entirely new breakthrough physics. Quantum Echoes was, in many ways, Willow proving it could do more than survive its own errors. It was Willow being handed a genuinely hard, scientifically meaningful problem, one that mattered to physicists, studying chaos and information, and returning an answer that matched theory well enough to be trusted. That combination, a chip stable enough to compute reliably and a problem meaty enough to matter, is why this particular result landed so differently than earlier, narrower demonstrations of quantum supremacy, a term researchers have mostly moved away from because it oversold what those earlier experiments actually proved. Some of the first supremacy claims, dating back several years, were criticized for solving problems that, while hard for classical computers, had little practical or scientific value beyond proving quantum computers could, in principle, outperform classical ones on some task. Quantum Echoes broke that pattern. It solved something physicists actually care about, using data that connects directly to open questions in quantum gravity and condensed matter physics, and it did so with a technique, the Echo protocol, that also happens to have a plausible path toward real-world chemistry applications. That's a rare combination in the history of quantum computing announcements, and it's a big part of why the physics community's reaction has been less, here's a cute demo, and more, we need to sit with this. It's also worth walking through, in a bit more detail, exactly how strange it is that scrambled information can be recovered at all, because this is the crux of why the word disturbing keeps getting attached to this story. Imagine an enormous, elaborate line of falling dominoes. Except instead of a simple straight line, imagine thousands of dominoes arranged in an impossibly tangled web, each one connected to dozens of others, so that tipping over any single domino sets off a cascade that eventually touches every other domino in the entire structure. Now imagine someone sneaks in and nudges just one domino very slightly, not enough to topple it, just enough to shift its angle by a fraction of a degree before the whole cascade begins. As the wave of falling dominoes spreads outward, that tiny nudge gets folded into billions of subsequent interactions, seemingly disappearing into the noise of the whole collapsing structure. If you looked at the final resting positions of all those dominoes, you would have no hope, none whatsoever, of identifying which one had been nudged, or by how much, using ordinary observation. The information looks completely gone, smeared across the entire system. What the Echo protocol does is the equivalent of designing the domino cascade, so that, after it finishes falling, you can run it in perfect reverse, every domino standing itself back up in the exact opposite sequence it fell, and when you do, that original tiny nudge reappears as a small but detectable discrepancy at the very end, a domino that doesn't quite return to its exact starting angle. The fact that this works at all, mathematically, tells you something profound about the nature of chaotic systems. Information is not destroyed by scrambling, only hidden, encoded so thoroughly across the whole system that reversing the process is the only way to retrieve it. And reversing a system with over 100 entangled qubits, each interacting with dozens of others through millions of possible pathways, is not something you can do with pen and paper, or even with the world's fastest supercomputers, within any reasonable amount of time. It requires a machine that thinks the way the scrambled system itself thinks, in superpositions and entangled probabilities, rather than sequential classical steps. This is also a good moment to address a very reasonable question that tends to come up whenever a story like this goes viral. Could any of this be exaggerated or even fabricated by hype-hungry media? It's a fair instinct, and a healthy one. The underlying physics here has been published through legitimate, peer-reviewed channels, cross-checked using known molecular structures and smaller-scale calculations that classical computers could independently verify, and discussed openly by researchers willing to put their names, their reputations, and their institutional affiliations behind the claims. That's meaningfully different from an anonymous forum post or an unverified rumor. At the same time, it's worth being clear-eyed about the difference between the actual peer-reviewed result and the layer of dramatic packaging wrapped around it for online audiences. The real finding is precise, narrow, and genuinely significant. A quantum processor measured out-of-time order correlators at a scale and speed no classical computer could match, using a technique with plausible near-term applications in molecular science, and in doing so provided experimental data relevant to deep theoretical questions about information scrambling in black holes. The phrase predicts the future, by contrast, is a storytelling device, an evocative but imprecise shorthand for traces how a small disturbance propagates through a chaotic system and can be recovered afterward. Both things can be true at once. The science is real and remarkable, and the headline is doing some poetic exaggeration to get you to click. There's one more thread worth pulling on before we close, and it's the thread that ties this entire story back to something deeply, almost uncomfortably human. Every civilization that has ever looked up at the stars, or down at a flame, or into the eyes of another person, has wrestled with the same basic question. Is the world around us fundamentally orderly, governed by rules we could someday fully understand? Or is it fundamentally chaotic, forever beyond our grasp, full of surprises no amount of knowledge could ever anticipate? For most of human history, that question belonged to philosophers and priests. Then it belonged to mathematicians and physicists, armed with equations, but no way to test the wildest of their ideas. Now, for the first time, it belongs, even if only in a small, carefully controlled corner of a lab, to an actual machine, one that can take a question about chaos and hidden information and hand back a number, a measurement, a piece of hard evidence. That is, in the end, the real story hiding underneath the sensational headline. Not that a computer has learned to see tomorrow, not that physicists have found some crack in causality itself, but that humanity has built for the first time a working instrument capable of directly probing the mathematics of scrambled information, the same mathematics that governs black holes, chaotic weather systems, and the deep unpredictability we associate with complex systems everywhere. It's a machine that can whisper a secret into a hurricane of quantum chaos, and then, remarkably, hear that secret whispered back. And whether you find that comforting or unsettling probably says less about the physics itself and more about how you feel, deep down, about living in a universe that might be far more precisely patterned, far less random than it has ever appeared to be.